North Atlantic. In the middle of the ocean stands a giant steel structure as tall as a skyscraper, surrounded by nothing but water and storms. Hundreds of people work on its decks around the clock. Helicopters transport crews hundreds of kilometers from shore, while beneath the platform lies a complex network of pipes and equipment extending deep below the seabed. Every day, thousands of tons of oil and gas pass through this structure. Any major accident here can cost billions of dollars, and any shutdown means losing an enormous amount of oil that the platform is designed to produce 24 hours a day. That is why some of the most complex engineering systems on the planet are hidden inside these offshore giants. Yet most people have never seen how these structures actually work. From the surface, they look like ordinary platforms in the middle of the ocean. But beneath the water lies a vast industrial complex whose true scale is difficult to imagine. Now you will see how the world's largest offshore oil platform operates, and what lies beneath the water under one of the most impressive structures ever built by humans. Imagine a massive city that engineers deliberately decided to sink into the raging ocean. That is exactly how the life of any oil platform begins. Everything starts on land, in a gigantic dry dock, where the lower part of the structure is cast from a special ultra-strong concrete. To prevent this artificial island from being crushed by the immense pressure of the water, its walls are reinforced with a dense network of steel rebar, while the structure itself is shaped into enormous hollow columns. A true monument to engineering is the Norwegian platform Troll A. Its foundation consists of 4 hollow concrete legs that inside resemble endless, gloomy shafts. The engineers intentionally left these supports hollow to house elevators and pipelines within them. Once the giant foundation is complete, the dry dock is simply flooded with water, and the concrete giant, weighing hundreds of thousands of tons, rises to the surface against all logic. Its enormous topside deck, complete with living quarters and drilling rigs, is assembled while it floats on the water. It seems unbelievable that such a colossal weight can stay afloat, but it is kept buoyant by ordinary air trapped inside the concrete chambers. When this concrete giant heads out into the open sea, a breathtaking spectacle begins. Moving an object with a total weight exceeding 1 million tons seems like an impossible task. For this dangerous operation, a fleet of the most powerful tugboats is brought in, connected to the platform by steel cables as thick as a human arm. The vessels form a special wedge-shaped formation and slowly pull the structure at walking speed. The most nerve-wracking moment comes during the first miles of the journey, when the giant passes through narrow straits. Any wrong maneuver or sudden gust of wind could drive the multi-million-dollar structure onto the rocks, destroying years of work. The ship captains operate at the very limit of their abilities, because if one of the tensioned cables snaps under load, the force released can instantly damage the vessel's equipment and put the entire operation, as well as the crew on board, at risk. Once the platform reaches its destination, the most spectacular phase begins: installation. To prevent it from becoming a drifting, uncontrollable vessel, it must be positioned over the drilling site with an accuracy of just a few meters. Engineers open valves, seawater rushes into the empty compartments with a thunderous roar, and the giant structure begins to sink slowly into place. These colossal structures are known as gravity-based platforms. They remain fixed in position solely because of their incredible weight. Once the concrete foundation reaches the seabed, its lower steel skirts are literally pressed into the ocean floor under the weight of hundreds of thousands of tons. After that, the space beneath them is filled with cement, permanently bonding the artificial island to the seabed without the need for any additional piles. The historic towing of the Troll A platform in May 1995 became a landmark event in engineering history. Standing 472 meters tall, the structure rose above the waves so high that its top extended far above the Eiffel Tower. When 11 tugboats began pulling this concrete giant into the North Sea, the entire country followed the operation live. The 200-kilometer journey took a full 7 days. Unofficial theories circulated in the press claiming that such an enormous mass of concrete could trigger a localized shift in the seabed, but thanks to the remarkable precision of the navigation teams, the operation was completed successfully. But another fascinating secret lies here. Even if engineers managed to secure this enormous structure perfectly to the ocean floor, how is it possible to sustain the lives of hundreds of people inside this isolated concrete fortress? And what systems allow this industrial facility to function like a living organism? Life on an offshore drilling platform depends entirely on electricity, without which this giant would instantly become nothing more than a pile of metal. Its energy heart consists of powerful gas turbines running on associated natural gas. A striking example of such self-sufficiency is the Russian Berkut platform, whose generators reliably supply power to industrial equipment and life support systems even during extreme freezing conditions. Special desalination units operate around the clock, turning tons of seawater into drinking water, while air filtration systems continuously purify the air throughout the facility. If the turbines were ever to shut down in the middle of a storm, the crew would have only minutes before critical systems began to freeze. Which is why a backup network of emergency diesel generators is always on standby. Every day at sea requires extremely complex logistics, since the platform is isolated from the mainland by dozens of kilometers. Delivering fresh food, medical supplies, and replacement crews becomes a carefully coordinated operation involving helicopters and supply vessels. Helicopters travel regularly between the shore and the platform, although their flights are heavily dependent on unpredictable weather, strong winds, and fog. Heavy cargo is delivered by specialized ships capable of maintaining position alongside the platform's supports even in rough seas, where deck cranes then lift multi-ton containers aboard. Newcomers sometimes hear alarming stories, claiming that prolonged storms could leave workers without food and trigger panic. But these are nothing more than myths, since every platform maintains emergency food reserves sufficient for several weeks. Inside this isolated environment, strict rules apply to everyone. Personnel work on a demanding two-shift schedule, where 12 hours of hard labor are followed by 12 hours of rest, with no days off for the entire duration of the rotation. The daily life of hundreds of specialists is organized with maximum comfort in mind. There are laundries, gyms, saunas, and dining halls offering 4 free meals a day. The cooks prepare varied, high-calorie meals to maintain the strength of workers who face intense physical demands every day amid constant noise and vibration. A striking example of engineering resilience is the way life is organized on the Berkut platform in the harsh waters of the Sea of Okhotsk. This facility withstands Far Eastern temperatures as low as -45 degrees Celsius and the tremendous force of drifting ice fields. In winter, when the sea freezes over, cargo deliveries by ship come to a halt, and the platform relies entirely on helicopter transport. All living quarters are protected by powerful thermal insulation, while deck heating systems prevent equipment from becoming coated with ice. Unofficial rumors sometimes circulate claiming that workers often see strange lights among the ice ridges at night. But engineers explain these phenomena as nothing more than the refraction of floodlight beams through ice crystals. Well-organized living conditions and a stable power supply provide a reasonable level of comfort on the surface. But what is it that hundreds of specialists risk their lives for every day so far from land? And what immense forces do they face when they begin drilling through the Earth's crust to depths of several kilometers? The process of penetrating deep into the Earth through a vast column of ocean water resembles an incredibly complex surgical operation performed in complete darkness from an enormous distance. To reach valuable fuel reserves, engineers lower a massive drill to the seabed, where it must cut through some of the hardest rock formations under tremendous pressure. The drill's path is controlled remotely using highly sophisticated electronic systems. Modern technology makes it possible not only to drill straight down, but also to gradually steer the drill sideways, creating remarkable directional wells. This allows engineers to reach underground reservoirs located several kilometers away from the platform itself, while drilling from a single location. A special, dense drilling fluid is continuously pumped through the steel pipe to cool the drill bit, which becomes intensely heated by friction, while also carrying crushed rock fragments back to the surface. On the ocean floor, directly above the point where the drill enters the earth, stands the platform's most important guardian, the blowout preventer. This device, weighing hundreds of tons, serves as the platform's primary safety mechanism, ensuring the environmental security of the entire operation. Its purpose is to monitor and stabilize reservoir pressure. If any abnormality is detected, this steel giant instantly activates a set of powerful hydraulic shears through an automated control system. These blades can easily cut through massive drilling pipes and completely seal the well, blocking the path of any uncontrolled flow rushing upward. When the extracted mixture finally reaches the platform, it is a dirty, turbulent blend of oil, flammable gas, corrosive water, and sand. In this state, the raw material cannot be sent to shore, so the first stage of processing begins directly on the platform, inside enormous vessels known as separators. Within these giant tanks, the raw mixture is separated into its individual components based on differences in weight and density. Heavy salt water settles at the bottom and, after thorough treatment, is discharged back into the sea, while lighter gas rises to the top and is partially used to power the platform's own turbines. The commercial-grade oil, purified of harmful impurities and sand, is pumped into transportation systems for delivery through subsea pipelines or into tankers. This continuous process operates around the clock, requiring operators to constantly monitor pressure and temperature within every processing unit. A remarkable example of these advanced technologies in action is the drilling of ultra-long wells at the Arkutun-Dagi field in the Russian Far East. There, on the giant offshore platform Berkut, specialists use a unique top drive system that makes it possible to create highly complex directional wells in the harsh conditions of the Sea of Okhotsk. The drilling equipment advances underground with extraordinary precision, covering vast distances from the platform itself, while successfully navigating around complex geological obstacles and high-pressure pockets. These advanced drilling systems are capable of controlling immense underground pressures. But what happens when the threat comes from the outside? Is the platform prepared to protect its vulnerable wells from the fury of ocean storms, drifting icebergs, and sudden fires? An offshore platform in the open ocean spends the entire year on the front line, facing the relentless forces of nature as its greatest enemy. Imagine colossal mountains of ice weighing millions of tons, slowly drifting with the currents and heading directly toward the concrete supports of this artificial island. Engineers designed these structures with such incredible strength that they can withstand direct impacts from wandering icebergs, as well as powerful seismic events reaching magnitudes of up to 9. The most terrifying and unpredictable nightmare for the crew remains the sudden appearance of rogue waves, born in the middle of violent storms and capable of reaching the height of a multi-story building. These walls of water carry devastating mass and can instantly sweep away any unprotected equipment on the lower decks. That is why the entire structure is designed with streamlined forms, while living quarters are elevated well above the danger zone. Steel and concrete walls literally groan under the impact of billions of tons of crashing water. But thanks to the flexibility of their internal support systems, the platform absorbs these tremendous blows, preventing the metal from cracking under fatigue. But while a thick layer of concrete and steel can protect against the external force of a storm, an internal threat, in the form of a sudden fire, requires completely different methods of defense. On a facility where highly flammable hydrocarbons are processed around the clock, even the slightest trace of smoke or a sudden rise in temperature causes sensors to instantly activate a powerful automatic firefighting system. Within fractions of a second, dense water curtains rise around processing units, blocking the spread of flames, while specialized robotic cannons begin flooding the fire with an avalanche of thick chemical foam that cuts off the oxygen supply. Every section of the platform is separated by sealed, fire-resistant barriers, capable of containing a raging blaze for hours. while the rest of the facility continues operating in emergency mode, giving personnel enough time to evacuate safely using lifeboats. A true legend in the history of battling the fury of the ocean is the Chinese deepwater platform Haiyang Shiyu, which regularly faces some of the most destructive Pacific typhoons. During one of the most powerful storms, giant waves more than 30 meters high slammed into the structure, putting every steel joint to the ultimate test. The platform endured extreme dynamic loads, rolling violently from side to side, yet it remained standing, thanks to a unique intelligent dynamic positioning system that kept the structure in place by automatically adjusting the thrust of underwater propellers. For hours, the crew remained in complete darkness inside the living quarters, surrounded by the deafening roar of the wind and the pounding of the waves, while the automated systems fought for the survival of the massive installation. At the time, the media was filled with mysterious theories, claiming that during the peak of the storm, sensors had detected a strange, giant object beneath the platform that supposedly dampened the movement of the water and helped stabilize its foundation. Of course, these turned out to be nothing more than fantastic rumors, born from fear of the elements, and the platform's survival was due solely to brilliant engineering design and the strength of its steel. The platform's protective systems effectively handle the known challenges of surface weather, but can they respond if the threat comes not from the atmosphere, but from the unknown depths of the well itself, where instruments suddenly begin detecting anomalies that defy the logic of engineers? At times, during the routine operation of drilling systems at great depths, events occur that make even the most experienced engineers uneasy. Several kilometers below the surface, where the drill penetrates some of the oldest layers of the Earth's crust, sensors periodically register sudden and abnormal pressure fluctuations. The drill seems to break into hidden underground reservoirs, where the equipment encounters enormous stresses. From these dark depths, strange acoustic vibrations begin traveling to the surface through the steel pipes, resembling a dull, intermittent rumble. Engineers provide a completely rational and strictly scientific explanation for this phenomenon, stating that the sounds are caused by sudden pressure changes, the collapse of compressed gas bubbles trapped within underground pockets, and the natural resonance that occurs inside a metal column stretching for kilometers. At such moments, the platform may enter its most extreme operating scenario, when the automatic emergency protection system switches into full emergency response mode. If sensors detect a critical change in conditions at the bottom of the well that falls outside the limits of the computer's predictive models, the system instantly shuts down the mechanisms to protect human life. At the command of the control system, the powerful pumps shut down within seconds, and the massive drill comes to a complete stop. The piercing wail of the emergency alarm echoes across the decks. As the industrial machinery falls silent during the emergency shutdown, an eerie stillness settles over the platform, leaving the drilling crew alone with the unknown, unable to understand what is happening several kilometers beneath their feet. The team must operate with absolute concentration, strictly following procedures and checking instrument readings while the massive blowout preventers hold back the immense pressure trying to force its way upward through the sealed wellbore. A similar alarming incident occurred on one of the deepwater platforms operating in the Gulf of Mexico. During drilling and subsequent production from a complex multi-phase reservoir, an automatic well control failure occurred. System pressure surged to critical levels within seconds, while instruments in the control room began displaying chaotic and contradictory readings. The automated safety systems functioned as designed and immediately sealed the well, but the shutdown completely halted production on the platform for several hours. Mystical rumors quickly spread online, claiming that the drilling crew had disturbed an ancient tectonic nest. But the official engineering report soon demonstrated that the incident had been caused by a simple combination of formation movement, a gas influx, and monitoring equipment clogged with drilling mud. What truly lies hidden within the ancient tectonic fractures of our planet, where humanity continues to push its increasingly powerful steel drills deeper year after year, every step farther into the unexplored depths beneath the oceans, forces engineers to create ever more sophisticated and expensive protective systems to control the unpredictable forces hidden below the Earth's surface.